Well, hello, Los Burros. How are you today? I hope you are enjoying learning some electrochem. So last time we talked about our standard cell potentials and how we can use that to that the electromotive force is the driving force for galvanic cells, but we can also use that cell potential concept to decide if all or if any redox reaction is spontaneous. If my E prime for the reaction is positive, then the forward reaction is spontaneous, and if E prime for the reverse is, excuse me, if the E prime is negative for the reaction, then the reverse reaction is spontaneous. So now we then want to take a look at something like this, where I've got a cell made from my iron 2 going to iron and nickel going to nickel 2 going to nickel, and we want to know what the delta G prime is. And so yes, thermodynamics is indeed related to um, my cell potential. So here we go. Let's write some notes if I can find out where my marker is here. Good. So I think we are kind of like a big four, right? And so let's talk about, how about redox and delta G? Let's get into our thermal and redox. And we did mention, last time I did say this, and that is that we have a relationship, right, with my E and thermal, right? We said that when my E for my reaction is greater than 0, then the forward reaction is thermodynamically favored, i.e., it is spontaneous, and that when my E for my reaction is less than 0, then the reverse reaction is spontaneous. And we know that spontaneity is related to thermodynamics, so that means there must be a relationship between delta G and E, and indeed there is. And that relationship is that delta G is equal to negative NFE. And so in this case, my E is my potential for the reaction. That's my reaction potential, right? And we know how to calculate that. Um, and that N is equal to the number of moles of electrons transferred in the redox reaction. And this is based on our coefficients in the balanced equation, the coefficients on the electrons in our balanced equation. So when we are doing our half cell balancing, and we say, hey, we have to make the electrons, we have to equate the electrons, and so that each half cell has the same number of electrons. Well, that's the N. All right, and then F is what we call Faraday's constant. Faraday's constant. Yeah, you physics people like Faraday, right? And it has a value for us. It is 96485, I believe. Yay, I got it. It is 96485. 96485, and that is joules per volt mole, joules per volt mole, or it is also equal to 96485 coulombs per mole of electrons. That's really how many coulombs a mole of electron carries. And so you could really think of it as this, right? I can think of it as you have 96485 coulombs equals 1 mole of electrons. That'll come back for us later, folks. So remember that. And it is what? This is the charge on 1 mole of electrons. All right, so that's what Faraday's constant is. And um, if E is equal to, excuse me, if delta G is equal to negative NFE, that would mean, of course, I could do that at standard conditions, and delta G prime is equal to negative NFE prime. There we go. Wunderbar. Isn't that wonderful? So let's do some work here. So I have a standard cell, and I want to know what the delta G is. So all I have to do is what? Delta G prime is equal to negative NFE prime. So I need to get my E. So what is my E? I'm going to write this down here. My E prime for that reaction is going to be equal to, what did we see in my galvanic cell? We have, as I recall, this was my anode from this, when we did this earlier in the chapter, and this is my cathode, right? And so that means this is my oxidizing and this is my reducing species. So that would mean my E reduction potential for my reducing species minus E reduction potential for my oxidizing species. So that would mean I want to get my E standard reduction potential for my nickel 2 going to nickel minus my standard reduction potential for my iron 2 going to iron. You guys have remembered this, but I haven't, so I'm going to have to go back and get that data. And so let's do that. What is it? Nickel and iron. Whoa, look at all that stuff we did before. How beautiful. Whoa, hey. Okay, so let's clean this up. And okay, so I'm going to find my nickel. Here's my nickel. Nickel is a negative 0.28 volts for my nickel. And then what was my other iron? Iron, Fe, iron. Make sure you get the right Fe. Iron going to solid iron is a negative 0.440 volts. Now I remember. Cool. Here we go. Oops. Back. There we go. So what do? I put this in here and I get a negative 0.28 volts minus a 0.440 volts, and that would give me a positive 0.16 volts for my E prime. So then my delta G, I have to look at how many electrons are transferred, right? So I better write my half reaction. So I have my Fe2 plus, excuse me, I have to rewrite that. That's not, Fe is what's oxidizing. Fe oxidizes to Fe2 plus, aqueous plus 2 electrons. My nickel 2 reacts with 2 electrons to form nickel solid, right? And so how many electrons are transferred? Well, that would mean 2 electrons are transferred, right? So my N is equal to 2 here. Good. So my delta G prime is equal to negative 2 times my F, 96485 joules per volt mole, times 0.16 volts. Yikes. There we go. I like it. Here we go. 2 times 96485 times 0.16. And what do I get? I get a 30875 negative, right? And this would be joules per mole, right? Or we could make this into kilojoules, and I should get my sig figs. I only have 2 sig figs, so that'd be what, a negative 31 kilojoules per mole, right? Cool. And remember, we said when this is a positive value, that it is spontaneous. And recalling from our thermodynamics, a delta G negative is spontaneous. So it would make sense that my values between my E and my delta G are opposite signs. Okay, you guys do the next one. Bring me back when you're ready. All right, here we go. Aluminum and my iodine. Once again, I don't remember what that is, so we'll go ahead and dig those numbers up. Aluminum and iodine. I like aluminum and iodine. Okay, aluminum is what? Aluminum is a negative 1.66 for my aluminum. My iodine is going to be what? 0.536. 0.536. Yeah, good. Oh, we have to go back, don't I? I forgot to answer a question. We'll get that in a second. So, aluminum, so my E prime for my reaction is, by the way, aluminum is doing what? Aluminum is oxidizing. Okay, so that means I want to take my standard reduction for my reducing minus the standard reduction for my oxidizing. So in this case, my standard reduction for the reducing would be my I2 minus the standard reduction for my aluminum, right? And so that's equal to, what did I say? A 0.536 minus a negative 1.66. And what does that give me? 0.536. Minus a minus is plus 0.166. And I get a 2.169 volts, right? That's what my E is. How many electrons are transferred? Well, we could write the we could write out our half reactions, right? I could do that, but I'll show you a trick. Notice I have aluminum going from 0 to 3 plus. So how many electrons does it take to go from 0 to 3 plus? Well, that means it's giving up 3 electrons. And how many times is that being done? Twice. Times 2, so that means I have 6 electrons that are being transferred in this reaction. So that would mean my N is equal to 6. So my delta G prime is equal to negative NFE, which is equal to E prime, sorry, which is equal to negative 6 moles of my electrons, right? Times F 96485 joules per volt mole times 2.196 volts. Right, good. And so what do I have? 2.196 times 96485 times 6. And that gives me, a really big number. 1271286. I'm going to divide that by 1,000. Divided by 1,000. And that gives me a negative, watch that, Kendall, a negative 1271 kilojoules per mole. How many sig figs? Looks like I could get, what? I can only get to my hundredths here, so 3. So my answer should be a negative 1270 kilojoules per mole. Ooh. Good. That is very spontaneous, isn't it? You think I did that right? Let's see. Let's just make sure. 6 times 96485 times 2.196. Yeah, that looks like a winner. Okay, divide that by 1,000. Yeah, I think I'm right. Good. There we go. Now, I kind of made a mistake. I kind of left something hanging here, didn't I? Because I never answered what is my equilibrium constant. So that means there must be equilibrium tied in with this somewhere. And indeed, there is, right? So let's talk about, let's see. Let's go with C. E, delta G, and equilibrium, right? You guys remember from from last chapter in thermodynamics, at equilibrium, remember we said what? Delta G is equal to delta G prime plus RT, the natural log of Q. You remember that? This was our adjustment for non-standard pressures. And then we said at equilibrium, though, so at equilibrium, we said that my delta G is 0, so then we have 0 is equal to delta G prime minus RT, the natural log, not minus, plus RT, the natural log of K, right? Because we are now, Kp, because we are now at equilibrium, my Q becomes my K, right? So that would mean what? Rewriting that, delta G prime is equal to negative RT natural log of Kp. But what else do we know? Hey, we know this right up here, which means that delta G prime is also equal to negative NFE prime. So then I could solve, I could solve for Kp, meaning what? Let's do this a little at a time. Let's divide both sides by negative RT, so my negative log of Kp is equal to NF over RT. You guys buy that? My negatives cancel. NFE prime over RT. Take the E of both sides, so my Kp is equal to E to the NFE prime over RT, right? And then you just have to make sure all your units work here, right? So my F is in joules per volt mole. My E is in volts. So my R needs to be in joules, right? So that means my R is going to be 8.314 joules per mole Kelvin. And then I need to have my T in Kelvin. All right? Cool. There we go. NFE prime over RT is how we can figure out my K. So here we go. Let me erase some of this so we can answer some stuff. Well, I don't want to erase too much. I think we're just going to come down here, right? Cool. So I want my equilibrium constant, and we know my Kp is equal to E to the negative delta G prime over RT, or it's equal to E to the NFE prime over RT. You can go any way you want about this. Kind of think we already have our stuff here, so let's go ahead with our E prime. So this is equal to E to the N. What did we say N was here? N was equal to 2,96485 joules per volt mole times what? My 0.16, which is my E prime, over R, 8.314 joules per mole Kelvin, times my temperature. We're at standard conditions, right? Let's look up here. Yeah, we're at standard conditions. So 298 K. So what's my E? What's my Kp equal to? Here we go. 2 times 96485 times 0.16 divided by 8.314 divided by 298. That gives me a number like 12.46. And then I'm going to take the E to the 12.46, and I get a big number, right? I get a 2580. That's not 258 300. I probably can only get 2 sigs out of this, so let's call it 260000 would be my equilibrium constant. You guys do the equilibrium constant right here. Okay, bring me back. All right, so we've already really calculated my delta G, right? So we can get my equilibrium constant, which would be my Kp is equal to negative delta G prime over RT, or, excuse me, e to the, or we could go e to the NFE prime over RT. I've already done the work for my delta G. I'm going to take the easy way out this time. So I have my e to the negative, which is already a negative 1271286, right? Because that is my joules per mole, right? Divide that by 8.314 joules per mole Kelvin times 298 Kelvin, right? And we're going to get a really big number here, aren't we? 1271286 divided by 8.314 divided by 298. And that gives me e to the 513th. And I can't solve that, but we know that is a gigantic Kp. All right, cool. Everybody good? Everybody good? Wonderful. Why don't we stop right here, and then we'll pick up the lecture next time on this thing. Okay, see you.